Good afternoon. I am Mr. Rich. Thank you for joining me for this video. Thank you for watching the video. We're looking here at the development of the Arctan Antiderivative template. It's very important because this specific template helps you negotiate or avoid trigonometric integration and jump directly to this specific antiderivative, which is so much more easy and quick to arrive at. Think back to your derivative concepts. You know, when you saw this inverse trigonometric function, the inverse tan, and you did its derivative, you knew you came up with this in terms of the derivative of that. Then there must be an integral out there which, if you saw something like this in terms of a integrand form, you could, by means of a integral, come back to an antiderivative which would somehow have this form in it. And if you look at that 1 over 1 plus x squared, you could very well look at something like this, a squared plus x squared, because this 1 here is certainly the same thing as 1 squared. You're literally looking at something like this, and then, you know, by means of this integral, we're looking at this. Therefore, there must be some template out there which will bring this arctan antiderivative, and you would have some sort of value here. Whatever this value might be has to be examined, and you would arrive at this much quicker than you doing trigonometric substitution technique, bringing in the tangent function trigonometric identity tan square x plus 1 equals secant square x, and doing all of that substitution. There is a good shortcut out there, and that's this, the Arctan antiderivative template, and we will see how we can arrive at it. But remember, it all stems from this loop that you see, the derivative and the integral loop. You are essentially seeing an integral which has this appearance, for which you in your mind are thinking the arctan antiderivative, because this should bring you the inverse tan or the arctan. How can you go about developing that template? Think about trigonometric substitution, and think about this particular identity, tan square x plus 1 is equal to secant square x. Tan square x plus 1 square is equal to secant square x. You would have some sort of value here which would mimic this in terms of the constant. Then you would have a certain x value which would be a tan theta, and then you'll have a certain derivative of that which would be a secant square theta d theta. You'd put all of these items here into this integral, and everything will come into effect momentarily with regards to that template formation. Remember, we're looking here at the template derivation, and then here in the denominator you'll have a squared plus a squared tan squared theta. You would isolate from this denominator the a square, and then you're looking at 1 plus tan squared theta. When you do that, this a and this a square can simplify. You can bring the 1 over a out, but then you're looking at a secant squared theta d theta, and then divided by secant squared theta, as you see right over here. Those secant squared thetas very well cancel out. You end up with 1 over a integral d theta. The antiderivative of this is just going to be a theta plus c, but this theta needs to be examined further, and we will. Everything will be examined with regards to this. You will have here theta is equal to arc tan x over a. This will very well substitute for right here. You'll have 1 over a arc tan x over a, and here is your template that you have been waiting for. This template will help you negotiate any of these type of questions right over here, and I will show you by erasing exactly what I have over here, because you've seen it now. Focus of this video is this template right here. We'll utilize it. Look at this question, dx over 11 plus x squared. Here I know a square is equal to 11, a square plus x square, but a is equal to root 11. Bring everything here into this template. 1 over root 11 arc tan x over root 11 plus c, and you're done. That's it. You could do this the long route using the trigonometric substitution route, and it would be just the same answer, but you'll go through a longer route. Let me show you one more example. 3 dx over 5 plus x squared. Here a square is equal to 5, but a is equal to root 5. You're plugging everything here, except you have this little constant which you pushed out, which is fine. That will very well take the place of this 1 here. You'll have 3 over root 5. Then you'll have your arctan antiderivative come into the picture by means of that. X over root 5 plus c, and here it is, done. This template is very wonderful because it saves a lot of time and effort. So remember this template for anything which has this appearance, and it can be modified. I've presented videos on complexity of the arctan antiderivative and some of the peculiarities that can arise with this form, but you still have a general template you have to utilize in those cases. For the basic cases of these forms right here, this template works excellent. Thank you for watching. Have a nice day.